Hello, my name is Tom Rummage here at the Applications Engineering Department of Micromeasurements, and today we're going to talk about the pyramid approach to strain measurement. Everybody knows what a pyramid looks like. It's one of those, you've been to Egypt or seen pictures from Egypt. It's a very, very stable architectural form, and the reason for that is it's got a really good foundation, and when you go up to the top you've got a nice peak. So we're going to start off with the foundation of strain measurement. First thing we have to define is the test program. Test program is basically what are we going to measure, and usually when I was working in the field I would get together the test engineer, the test technician, and the analysis people who are asking for the data. And in that meeting we would come down to what is it we're going to measure, how are we going to measure it, and then how are we going to report it. So you start off with a test program, and we have a form here, how to define a test program, where you put down the parameters of the temperatures and the material you're going to be using and all the parameters that it might have any influence on selecting the adhesive or the strain gauge or the environmental protection that's associated with it. So at this point, we're going to go into starting the test program. We're going to look at the specimen. Okay, the specimen, there's a couple of concerns. The first one would be solvent sensitivity. If you have a plastic or non-metallic part, they can be dissolved or degraded with some of the chemical solvents that we use to degrease our products, especially the polycarbonates or the ABS materials. You might want to consider using 2-propanol, a reagent grade of it, our GC6, as the degreaser on those materials. However, you want to make sure your degreaser does not, whatever you use, does not leave any residual material behind. You take a glass plate and you clean it thoroughly, then put your degreaser of choice on it and allow it to evaporate. If it leaves behind any sort of a powder or a residue, then you probably shouldn't be using that on strain gauges for a solvent material. The next area of concern is its coefficient of thermal expansion. Well, why in the heck do you want to learn about how big it gets or how small it gets when it gets hot and cold? Well, that looks like strain to the strain gauge, and we will talk much more thoroughly about STC, or self-temperature compensation, later. We also have to consider the porosity of the material. Is it a concrete or a composite material with a woven surface or a rough surface? Strain gauges do not like to conform to very irregular surfaces, so you might have to consider either removing that porosity, gray cast iron part, grinding away the surface, or filling that material using an adhesive system like AE10 or GA2 as a filler to fill up the surface and then sand it back to just get back to the parent material. We also have to consider temperature limits during the specimen concerns. How hot or cold can you get it? If you use an elevated temperature cure adhesive system, are you going to end up with a puddle of plastic in your oven at the end of the day, which usually is fairly upsetting? Or are you going to use it on a material like aluminum? And if you go to high temperatures for aluminum and stay there for a very long time, let's say you had 2024 T4 aluminum and you stay at 500 degrees for 2 or 3 hours. Is it 2024 anymore? No. I'm not a metallurgist. I can't tell you what it is, but I can tell you it's not the same material properties. So we have to pay attention to the things like solvent sensitivity. We need to know its coefficient of thermal expansion to be able to match that to the self-temperature compensation of the strain gauge. If it's a porous material, we have to decide whether or not we're going to remove that porosity or fill it. And we also have to understand the temperature limits of our material. We don't want to change the material or the test article by applying the strain gauge. Next thing, surface preparation. If you get this right, everything's going to go fine. If you get this wrong, you're going to have trouble. There's a number of things that we want to consider. The first of which is the RMS surface finish. How rough is the material? A lot of people think, they look at a polished piece of aluminum and go, wow, that's the perfect strain gauge installation technique for surface, right? Well, no. Strain gauge has to have something to grab hold of. I like to use the little analogy, take your average house cat, plop him down on the windshield of your car, drive down the road at 10 miles an hour and slam on the brakes. What happens to the cat? He slides off and he's a very unhappy animal. He didn't have anything to get his claws into on that windshield. Take the same cat, if you can catch him, put him back on the windshield and make that windshield out of a porous material, something out of wood or something that he can get his claws into, run down the road at 10 miles an hour, slam on the brakes, the cat's still there. The point is, the adhesive system must have something to grab hold of. If your surface is too smooth, you will limit the amount of elongation that you can get for a single elongation. In general, we shoot for somewhere between 60 and 120 RMS. That means the peak to valley measurement in microns for most stress analysis applications. If you're going into something like a post-yield study where very high elongations are anticipated, you might go with a much more coarse finish, something with maybe 80 or 90 grit silicon carbide abrasive paper to make it real coarse. But important is that it must be a uniform surface and have a uniform surface roughness appropriate for strain measurement. The next thing when we are talking about surface preparation concerns is what is the pH value of the surface of our material. Our cyanoacrylids, and all cyanoacrylids for that matter, are very sensitive to pH. If you put the surface, when you finish your surface preparation and your last step is our conditioner A, a mild phosphoric acid solution, which it should never be, by the way, then you try and bond with M-bond 200, I can almost guarantee a lack of success. The last step in almost all of our surface preparation should be the use of neutralizer 5A. This is an ammonia solution that allows you to get the pH to either nominally neutral or slightly basic. And all of our adhesive systems appreciate the fact that you have a pH of either 7 or higher, typically. Another consideration is surface contamination, and specifically silicon contamination. A lot of machined parts use a free silicon cutting oil that helps to reduce the friction and the heat and the damage to the cutters. But in terms of bonding a strain gauge, free silicons are a very, very serious problem. If you are able to and you're going to machine the part, ask the machine shop not to use a silicon-based cutting oil. If, however, they have to do that and you do have silicon contamination, the very best solution is to heat up conditioner A to as hot as you can stand it, and you scrub a very large area. Then rinse it off. Then scrub a smaller area, rinse it off. Scrub a smaller area, rinse it off. The reason is the free silicons tend to migrate, and by starting with a bigger area and going smaller and smaller and smaller with your scrubbing with the conditioner A, the better off you're going to be in terms of getting rid of the free silicons. Best way is to avoid them in the first place. There are a number of other parameters that might affect your surface preparation and or all the materials that would you use to do that. They can be found in our Bulletin B129, Surface Preparation for Strain Measurements. This includes a list of all the different materials that we have documentation and whether you should use a degreaser, conditioner, neutralizer, air abrades, that kind of thing. All of those things are detailed in this particular document. So if you're worried about that, go to our website, look up Bulletin B129 under our resources place on the website, and you can find it there. The next thing is the adhesive system. We've talked about the surface preparation. We've got ready to put the gauge down. Now we've got to decide what adhesive system would be appropriate for our application. Okay, back when I was in college, I had a list of things that I wanted in a wife. I wanted particular parameters for her to be. She needed to be able to cook. She needed to be nice looking. She needed to be able to be articulate. And the last thing and the most important, she had to tolerate me. Early on in that search for a wife during my early college years, I determined that I'd have to make a few compromises. The same thing is true of the adhesive systems. Ideal adhesive system characteristics. It'll form a permanent bond line with any specimen or any strain gauge backing. It will be simple to mix and use in the field or the laboratory. It should have sufficient pot life and handling time to allow for an application of a large number of strain gauges. Could form a very thin, void-free bond line with good shear rigidity and transmit strain without creep effects. And finally, the last overall general characteristic would be operate from deep cryogenic temperatures all the way up to the highest temperatures selected. Excuse me. The ragweed in North Carolina is blooming. Okay, those are ideal characteristics. Now, let's talk about the individual types of adhesives we offer. The first one, and probably the one that's used in 90% of the stress analysis applications around the world, is a cyanoacrylate. The cyanoacrylate adhesive systems are a single component liquid that'll cure in 1 to 2 minutes when spread into a thin layer. It has a large number of sensitivities. It can't get too hot, it gets soft. It can't be exposed to too high humidity, it gets soft. Over a long period of time, this is considered a temporary adhesive system. Over a long period of time, this material will continue to embrittle, and eventually at somewhere between 9 months and a year, when you go to too high of elongation, it might fail. The bond line might fail. So it is considered a temporary adhesive system, but because of its ease of use and its performance, it's used and relied on by a large number of our stress analysis customers who are doing room temperature testing. Excellent material. However, be sure and select a qualified for strain measurement cyanoacrylate. Don't go down to your local hobby shop and pick up that Zap-A-Gap off the shelf and say, oh, that looks good enough. It looks the same as the M-Bond 200. Well, for every 10 batches of adhesive we receive here from the vendors that we buy it from, we'll reject between 5 and 6 of them because they're wrong viscosity, they don't have the proper cure properties, they don't transmit strain appropriately, etc., etc., etc. So we would encourage you, if you're going to buy a cyanoacrylate for your adhesive system for your strain measurement, that you do so from a qualified strain gauge vendor. Don't just go out to your local hobby shop and buy it there. The next adhesive classification would be solvent-thinned epoxies. Solvent-thinned epoxies are similar of our M-Bond 600, 610. These require an elevated temperature cure. They're the favorite of transducer manufacturers, and the reason for that is they have a much longer pot life, somewhere between 2 weeks and 6 weeks, depending upon the material you're using, and they're very repeatable. If you use the same manufacturing steps, including the clamping pressure, the ramp rate on the cure temperature, the maximum cure temperature and the time you stay there, and then the post-cure, the first transducer you build and the 10,000th transducer will build based on the adhesive system will be identical. Again, it's a favorite of the transducer manufacturers because of its repeatability and its high strength, and it's a good low creep material. The next adhesive system would be the epoxies. The epoxies are an epoxy resin with a hardener that causes a polymerization to a thermoset solid. They're typically either room temperature curing or very low temperature, elevated temperature cure like the M-Bond AE10, which requires 125 degrees Fahrenheit. It is considered, and I hate to use the word permanent, but a permanent adhesive system because it does not have the limitations of M-Bond 200 of embrittlement. However, it will perform, assuming you stay within the parameters of the adhesive, both in temperature and elongation, it should be good for many, many years of operation. It requires a clamping pressure of 5 to 20 psi of clamping during that cure process, and that is typically going to be somewhere between 6 and longer hours. We typically recommend you cure at room temperature overnight. If you're going to elevate the temperature, be sure and understand your bond line temperature. That's not the oven temperature, it's the bond line temperature. Take a thermocouple, excuse me. Take a thermocouple, put it under the silicon gum pad and aluminum backing plate that we use for the clamping, and monitor the bond line temperature. This gives you a relationship between the cure time and the cure temperature. The epoxy systems are famous for their high elongation capabilities too. At room temperature, AE10 can do between 6 and 7% strain easily, and AE15 will do up to 10% strain at room temperature. We're understanding that 1% strain is 10,000 microstrain. That's a lot of strain. You're doing some sort of post-yield study, likely as not, or a very low modulus material. All right, let's talk about some of the parameters that you would use to select the adhesive system. The first thing, and probably the one that's going to be most critical, is its operating temperature range. And I'm looking at here the data sheet for M-Bond AE10, and its operating temperature range is -320, call that liquid nitrogen, all the way up to 200 degrees Fahrenheit, boiling water. You can extend that above 200 degrees Fahrenheit, but at that point it begins to get a little creepy. The bond line will get a little soft, and so you might have a problem with static measurements. But dynamic measurements all the way up to a couple of hundred degrees Fahrenheit is quite easily. Elongation capabilities based on temperature. At the -320, the lowest temperature for this particular adhesive, you can get about 1% strain, or about 10,000 microstrain. At room temperature, it'll go up to somewhere between 6 and 10% strain. As you can tell, you can do a post-yield type study. At elevated temperatures all the way up to 200 degrees Fahrenheit, it's good for up to 15% strain. So it's depending upon the temperature range, you select the adhesive system and the strain range that you're anticipating your test to go to. Shelf life. All of our adhesive systems have some sort of a shelf life, and all of our adhesive systems can have that shelf life extended if after you receive it, you immediately put it into the refrigerator. For instance, the AE10 has a 12-month shelf life at room temperature, but if it's stored at 40 degrees Fahrenheit in a refrigerator, it goes up to 18 months. You've basically made your shelf life 1.5 times longer than it was before. The important thing to remember, however, is when you take it out of the refrigerator, be sure it is up to room temperature before you open it. If it ingests moisture because of the condensing humidity of the air of the day, you might end up killing the adhesive system. What I recommend you do is take it out of the cabinet the night before, sit it on your desk, and that way it's up at room temperature, no problem. Almost universally, however, you'll forget to take it out of the refrigerator. What do you do the next morning? Some people will say microwave. Don't do that. It's not a good idea. Take the sealed container of the curing agent and resin, make sure they're very tightly sealed, stick them in your pocket. Leave them there till you can't tell it's there. Ooh, that's cold. Wait a minute, wait, I don't know it's there anymore. Then they've reached room temperature or above, and it's safe to use them. Never put them in an oven, never put them in a microwave. Don't put them into boiling water to warm up the resin because they are very sensitive to moisture. Pot life. Now this material, AE10, has a pot life of between 15 and 20 minutes. Now that's a fairly short pot life, so you got 10 grams of material here. You'll never use all of that material in the 10 to 15 minute pot life. You can, in this particular case, extend the pot life by taking a chemically clean aluminum plate or some good heat sink material that's chemically clean, pour the adhesive out on it and allow it to spread out. This sucks away some of that exothermic reaction or exothermic heat involved in the reaction and slows it down. That might give you another 10 or 15 minutes of pot life. If you're in Brownsville, Texas in the summer and it's 110 degrees in the shade, the aluminum plate's not going to help. Okay, you're just not going to be able to slow that reaction down. The last thing, and this is most important, is clamping pressure. I had occasion for a customer to call me up and say ugly things about my mother. He was upset with me. He had just bonded 40 strain gauges and came out the next day to take off the clamping pressure and look at the gauges, and all 40 of them came up with the tape. Needless to say, he was unhappy. We talked about his surface preparation. We talked about how he mixed the adhesive. Everything he had done was to the book. It was perfect. And then we got to clamping pressure. And he said he used 20 pounds. And I said, 20 psi? He says, no, it's a 20-pound weight. And over what? And I asked him, what square area? He says, well, it's one of your GT14s, which is nominally about 1/3 of a square inch. So he had 20 pounds of pressure on 1/3 of a square inch, so he's making 60 psi. And it clearly states in the instructions, to 5 to 20 psi. He had overclamped it by about 3 times. What this did was it starved the bond line. It's pressed it so thin that no matter what he did, when he tried to pull the gauge up, there was not enough mechanical material left in order to keep the gauge in place. Once we discovered this, he changed his clamping pressure and everybody was happy. Cure requirements. If you look at almost every one of our data sheets that come with adhesive systems that could require an elevated temperature cure, there's going to be a little chart. And this chart will show the minimum cure temperature. In this particular case, it's 75 degrees Fahrenheit, and run it up to about the maximum cure temperature. In this case, it's around 200 degrees Fahrenheit. At the 75 degrees Fahrenheit, it takes 6 hours to cure. At 200 degrees Fahrenheit, it takes 30 minutes. So you can accelerate the cure of your adhesive system if you understand the bond line temperature and the time that you've been there. And those are the characteristics that would make the selection of your adhesive. Let me review those again. First, operating temperature range. How hot or cold is it going to get? Second, what kind of elongation capability do you need? Do you want to go to high elongations, and are you going to do so at a deep cryogenic temperature? You might want to look at review the elongation requirements at deep cryogenic. What is its shelf life? How long can you store it? Can you extend that with refrigeration? What is its pot life once you mix it? AE10 has a pot life of 15 to 20 minutes. M-Bond 610 has a 6-week pot life. Obviously, there's a significant difference. Clamping pressure. All of our adhesive requires some sort of clamping pressure. M-Bond 200, third of a white thumbnail. It's a calibrated value. Just press down it with your thumb. AE10, AE15 is going to be 5 to 20 psi. The M-Bond 600, 610 family is going to be between 30 and 40 psi, typical. Cure requirements, be sure and review the cure requirements. If it requires an elevated temperature cure, will your part tolerate that and without any change in its physical parameters? Can you keep it at that temperature and hold it at a uniform temperature? Do you have an oven? Some cases you can use heat lamps. Some cases you can take a cardboard box, line it with aluminum, put a bulb in it, and turn it on and off when it gets hot and cold enough. I've had to do that before. But the important thing is to understand your bond line temperature and the time at that temperature, and make sure that that matches the chart that comes with the instruction bulletins for each adhesive systems. And there, my friends, is the end of the adhesive systems.